Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In the previous module, we discussed a generic optical fiber communication system, a point-to-point optical communication system, and then we looked at the modulator structures which can be used to modulate any of the carrier characteristics such as amplitude, phase and frequency. Although as I have told you, in this course we will be looking at only those modulations which will change the amplitude and phase in what is called as quadrature amplitude modulation. That is the modulation technique that we are going to discuss in detail, because that is the prevalent technique which is used today in almost all optical fiber communication systems. Now, if the change of the carrier characteristic is continuous, or it is analogous to whatever the change that the information is undergoing, where the information is usually a continuous time signal, then what we have is the analog communication system, and you can actually perform analog communication system, or you can implement analog communication system by biasing the modulator, the intensity modulator at what is called as the quadrature point, that is at point V pi by 2. If you were to bias and then apply a small signal which is continuous time, then your output intensity will be kind of faithful reproduction of the message signal. Okay. Of course, when the message signal is 0, the output will be non-zero, it will be having some amount of power coming out because you have biased it at the quadrature point of the modulator, and then when the input signal changes, then the output power will also change. So, that is the analog modulation. And as I have told you, analog modulation is something that is not quite preferred in today's optical communication systems, and in fact, in many of communication systems today, communication is mostly digital communication system. In digital communication system, the message signal is not continuous, rather it would be represented by binary numbers, that is a sequence of ones and zeros, and you can either code 1 0 with a waveform or 1 with a waveform, or you can take the groups of these zeros and ones and give an appropriate waveform or generate an appropriate waveform for it. And at the output, you just have to sample the received signal. Okay. Of course, when I say you just have to sample, there are a lot of operations that need to be taken place in the receiver, which some of those operations we are going to talk about it, but the net result of that receiver is that you are going to sample the signal, and by looking at the sample, you should be able to guess which of the group of bits that were transmitted, or in case of a single bit being transmitted in terms of a waveform mapping, then you are essentially looking at what was actually being transmitted, whether it was a single bit or a group of bits, depending on the sample value that you have received. Okay. Because information and the reception is not exactly continuous, it is in the form of bits which are kind of discontinuous or discrete. This is called as digital modulation, and digital modulation is what we are going to study mainly. However, even though we are using digital modulation, the signal that comes out of the optical transmitter will still be a waveform. Of course, it will be a waveform in the form of an electric field, which will then be coupled into the optical fiber after shaping a little bit of that signal that comes out of the transmitter, and maybe combining it with other channels that are present in the same system. But in the fiber, as soon as this signal is coupled, the signal is actually a continuous time signal. So, although we do talk about discrete levels and other things, the actual waveform that is being propagated from point A to point B is continuous. But luckily, we do not have to track over all the changes that the pulse is undergoing as it propagates, the pulse being representing some amount of information, representing the digital information. You do not have to keep track of every aspect of the pulse, because at the end, at the receiver, you are going to simply sample the signal and use the sample. So, which means that if the pulse changes its amplitude slightly, or gets distorted a little bit, it is all right, because we are not interested in those small details. But as long as these distortions and changes are not too drastic to change the pulse shape itself, then you are almost okay, and this is the reason why digital communication offers a higher immunity compared to analog communications. Okay, we talked a little bit about analog communications, we talked a little bit of digital communications. We need some mathematical tools to discuss further, and this module is actually concerned with review of some basic concepts in both deterministic and random signals that you would have seen, but perhaps kind of not being familiar right away. This is a good refresher, but because of the nature of this course being not the focus on these concepts, the review will be very fast, that is the pace of the review will be fast, but these are standard topics in undergraduate communication systems. So, you can actually look at any standard textbook and then brush up your knowledge of these concepts. So, with that caution caution that I have given you, let us look at some concepts that are absolutely critical, which will allow us to represent, to talk about the signals, and then to study what happens as the signals pass through different elements of the optical communication system, what happens when noise is added, what exactly is noise. All those things we are going to review by first stating that signals actually come in two varieties. A signal is essentially a function of time. We have used these signals a lot in optical communication systems as well. We had, for an optical fiber, we had a certain pulse that was transmitted, and at the output you had a pulse, and the shape of these pulses were different because of the dispersion in the fiber. But nevertheless, we did represent the electric field at the input of the fiber as a way, as a time domain function, and this time domain function presumably carries some information. Therefore, this can be considered as a signal. In this case, this is an optical signal or an electric field, and at the output again you had, at the output of the fiber you had for z equal to L, you had another time domain function which was E of L comma t. So, these are all signals which hopefully convey some amount of information to you. If we consider a simple signal such as x of t, this signal x of t could be of two types broadly. Okay. One is the deterministic signal and the other one is the random signal. A deterministic signal is one whose properties are reasonably easy to predict, or rather in fact a proper deterministic signal is one whose properties can be specified to any accuracy as you want, and if these deterministic signals pass through deterministic systems, that is transformations that would take x of t as input and transform it into some output which we will denote as y of t. So, if this rule of transformation or mapping is actually kind of fixed, then you actually have a deterministic system, and once you have been given a deterministic signal x of t and the deterministic system transfer function or the impulse response of the system, then it is easy to find out what will happen to y of t. Now, it would have been very nice for our communication system to have been composed only of deterministic signals and deterministic systems. Unfortunately, that is not the case, okay, because you may actually have. So, for argument's sake, I am going to assume that the fiber is deterministic. So, if I have sent in a pulse, I know exactly what will happen to the pulse at the output, but this is the pulse that is, I am not going to measure this pulse right here, right. What you are actually finding at the output of the fiber is the electric field, and to convert electric field into something that can be measured in the form of a current, you will have to use a photodiode, right. So, once you use a photodiode and there is some resistance RL which is the load resistor, let us say you are monitoring the output across this resistor RL. So, this optical pulse which is sent into the photodiode would then generate a photocurrent, and this photocurrent would multiply through the load resistor RL to generate the photo voltage, so to speak. But unfortunately, a real resistor, this is your RL which is an ideal resistor, but a real resistor is actually a physical resistor. It is made out of physical elements, and these elements of course are atoms coming from whatever the materials that are used to make up a resistor, and these physical resistors, because they are atoms and other things, they actually have some kinetic energy when the temperature T is greater than 0, and you know that one of the properties of these atoms is, and the electrons that are there, is that if they have been given some amount of energy, then they would like to jump from the valence band and go into the conduction band. Okay, I am just assuming that these are crystals, so therefore I am talking about band structure here, but it is not really necessary that way. So, the idea here is that if whatever material that you take, if its temperature is greater than 0, then there is an associated thermal energy which will then be imparted to the electrons, which will then allow these electrons to move. So, it will move, collide with the atoms and then come back to rest, and because there is some energy again available, it will move. So, there are these random motions that keep happening in the resistor, giving rise to what is called as a thermal noise, right. And this noise is an example of a signal that is random in nature, which means that if I were to measure this thermal noise across a resistor with an ideal voltmeter or whatever the meter that I am using, right, and if I have no other uncertainties in this measurement scheme, that is I have fixed the measurement correctly, I have the voltmeter also working correctly, the value that the voltmeter will actually show is not predictable. That is, if I look at the value, I know what is the value, but beforehand I cannot say with 100% certainty that this will be the amplitude of the voltage that you are going to measure, and I cannot do this. Even if by chance I am actually correct once, it does not matter much, because if I were to repeat this experiment a million and a million times, then my chances of predicting or being right will actually drastically go down, okay, because I cannot predict the amplitude, but I can predict that the amplitude would more or less be this particular value on average. That is, I look at results of million of experiments and then I say on an average the amplitude should be 3.5 microvolts, and the variance, that is the deviation from this average, be bounded to about plus or minus 1 microvolt. I mean, I can say these statements, and when I am making these statements, I have a picture in my mind in which these type of experiments are being repeated a million times, indicating that I am not able to give the results of one single experiment, but on an average I can predict the properties of these noise processes as well. So, the difference between deterministic and random signals is this: whenever I perform an experiment with a deterministic signal passing through a deterministic system, I can always predict the output no matter how many times I repeat that experiment. On the other hand, if I take noise, which is an example of a random signal, and then I pass it through a deterministic system, let us say the system is known very well, but because the input itself is unpredictable, the output is also not predictable, and therefore, the output is also random. So, that is not precise, but that is as close as we will get to define what is a random signal and what is a deterministic signal. Okay. In our modulators in the communication system, you can represent the output of a laser, okay, as the electric field E of t. For now, let us ignore the polarization aspect of it, and this output can be given by say square root of P s e to the power j omega 0 t, okay, and where omega 0 is of course the carrier, and I am using what is called as the complex notation. So, the signal that comes out will have to be a real signal. So, let us say this signal is about root P s cosine omega 0 t, as it would be. I can't obtain e to the power j omega 0 t as the output, but I do not want to keep writing cosine and sine. So, therefore, this is a shorthand notation that we use to represent the output that would come out. So, and this is in fact related to what is called as a phasor, and in terms of the phasor you can also write down, you can write down whatever the signals that are coming out of the transmitter, and further as they propagate to the various elements, you can look at what is happening to these phasors or to these complex signals and analyze the system. Okay. So, let us just, before going back to the complex domain, so let us actually look at this square root P s cos omega 0 t. Now, this is my carrier, correct. So, this is the carrier that I have, and here the two parameters that you can see are this power P s. I have used square root because I am writing the amplitude out there, and then I have omega naught, which is the carrier frequency. If these two are well defined and they actually have a unique value, then the carrier will be a deterministic signal. Unfortunately, this is an idealized expression, because I have to account for the fact that this omega 0 itself can be a function of time, called as the drift of the central frequency in the lasers, and moreover the spectrum will not be exactly a impulse like spectrum centered at omega 0. In fact, there will be a small amount of skirt around this frequency omega 0, which will then cause a certain noise to appear, and this noise appears, noise remember is just another function, but that function is non-deterministic or random in nature. So, that noise would appear here as what is called as the phase noise of the laser. Okay. So, in the complex representation, that would be e to the power j omega 0 t plus theta n of t. So, you can in fact write down that the overall phase psi of t of a non-ideal laser. So, this was a non-ideal laser or non-ideal oscillator will be the linear phase that comes because of the central frequency plus theta n of t, which is the phase noise, plus delta omega of t times t. Of course, I could have combined omega 0 and t and delta omega of t into t, but that anyway is okay, all right, we can put them separately out. So, this of course is the deterministic linear phase that you are going to get. If the laser were to be ideal, then the other two terms would not exist. If you were to plot this psi of t as a function of time t, it would be a straight line passing through the origin, and the slope of this would have been equal to omega naught. But because of the phase noise, this total phase will not be exactly same, it will be having some kind of a change or different slope and other things. And if delta omega of t, which would then refer to the which is usually referred to the frequency drift, what the effect of this frequency drift is to actually change the slope, right. So, you may actually have this kind of a behavior. Over time the slope may actually change. So, maybe this is also another behavior, and as you can see, I cannot write down a single graph and then say this is how the total phase would change, because all these terms theta n of t and delta omega of t times t are random signals. Okay. So, that is what we actually have. Anyway, so as this laser comes out, you are going to modulate the laser, correct. So, you are going to modulate the laser with whatever the modulation signal that will be there. So, let us say the modulation signal is some m of t. It does not mean that m of t is a continuous time signal only, it could be a discrete time or digital signal as well, but that is we have just at this point left it as it is. So, what will be the output of this modulator? Well, depends on what kind of modulation we are performing, right. So, but if you were to consider a simple double sideband suppressed carrier type of modulation, so what you have to do is to imagine that this m of t is going to multiply this carrier, which I am going to write this as square root of p s e to the power j omega 0 t, and for now I am going to imagine that this theta n of t and delta omega of t are equal to 0, okay, because I want to first look at what happens to the deterministic case and then come back to the random case. So, here is what I am doing. So, I have this m of t, and then when it gets multiplied to this carrier, you get square root p s e power j omega 0 t m of t. Okay. This is a signal that would come out. Now, in terms of frequency domain, what exactly has taken place? So, this is your multiplier, this is your carrier. Now, square root p s e power j omega 0 t is will have a spectrum which is centered at omega naught, and its spectrum will be a sharp peak at omega naught called as the impulse function here. It will have an amplitude of square root p s, but you do not really need to worry about the amplitude at this part, at this point. So, when this spectrum goes through, and then you have an m of t signal multiplying with respect to multiplying this input signal or the input spectrum here, we need to specify slightly more about this m of t. Let us assume that this m of t spectrum would look like this. Maybe this is deterministic or maybe it is not deterministic, but you can assume that this is the spectrum that would be coming out of this m of t. For now, we will just take it to be deterministic m of t. Okay. So, I have this m of t spectrum. Let us assume that the spectrum is centered at 0 frequency, okay, and instead of working with omega, I will switch and work with the frequency f. So, similarly, the carrier will not be omega 0, but it would actually be f naught, okay. And then the maximum m of f. So, this is m of f. I am only showing you the absolute spectrum, the phase spectrum I am not showing at there, but it will be there, okay. So, it will have both magnitude as well as phase spectra. So, we will assume that the spectrum is non-zero only over this band which is say from minus W to plus W, and because the significant spectrum is concentrated around 0 frequency, this is called as base band signal. Okay. That is, this is the spectrum is that of a base band signal. So, m of t is a base band signal, and then it has a bandwidth of W. Okay. So, it has a bandwidth of W because the maximum frequency is W hertz. Okay. So, it has a bandwidth of W hertz, and why did I write W and not the total width 2 W? Because in baseband signals the bandwidth is counted only from positive frequency part. Okay. So, it will be 0 to W. So, this is bandwidth of W hertz. Okay. And this operation of multiplication by the square root, what it would do is to take this baseband signal and then shift the center of that one, shift the center, instead of at 0 it would have shifted the center to f0. So, what you now have is an impulse f naught, but of course, you do not actually get to have the impulse the way I have written it. So, this is just used to place hold where f naught is, this is on the f axis of course, and then around this will be your baseband spectrum. Okay. So, around this is your baseband spectrum of whatever the bandwidth that you now have. The highest frequency here will be f0 plus W, the lowest frequency here will be f0 minus W. I am of course assuming that f0 is much larger than W, okay, and this signal which I have shown has only positive frequency components, and therefore, of course, is complex, is not really going to be there in our actual signals, because in actual or systems, in actual systems you will have not e power j omega 0 t, but you will have cos omega 0 t or cos 2 pi f naught t that would be multiplying. So, therefore, the spectrum of the carrier would be having 2 impulses, the amplitude of course will reduce by half. Okay. This is all coming from simple Fourier transform theory that you must be familiar with, and if you look at the carrier has 2 impulses, one at f naught and the other at minus f naught, and when you multiply that one with m of t, you are going to shift the spectrum m of f into 2 portions, one to the right that is centered at f naught and the other one centered at minus f naught. So, again you will have your baseband signal, both will actually have the same amplitude, this will have the same amplitude, and this frequency will now be minus f naught plus W, and this one will be minus f naught minus W. So, this signal which we have written, let us call this signal as x of t and the spectrum of this one as x of f. And if you look at the significant spectral content of x of f, that does not occur at 0 hertz, rather it occurs at f0 which is greater than 0 hertz, and therefore, this is called as pass band signal, sometimes also called as band pass signal. Usually this band pass signal or pass band signals are not represented in this manner, because you do not want to keep carrying around everywhere e to the power j 2 pi f0 t. So, rather you want to be able to talk about what is called as the canonical representation of the band pass signal. So, canonical representation means that any band pass signal whose carrier frequency f0 is greater than 0 and usually much greater than 0 can actually be written as x of t as the real part of x tilde of t e to the power j 2 pi f0 t, okay, where this x tilde of t is called as the complex low pass equivalent signal. Okay. The complex low pass equivalent signal, and this is the complex low pass equivalent of the band pass signal. So, in terms of pictures, this was the band pass signal that I had, and if you were to obtain the equivalent low pass signal of this one, which in this case turns out to be the m of t signal, but in general you do not know, if you do not know m of t, that is fine, you can start with the band pass signal and then go back to the base band. So, when you do that band pass to base band transformation or transition, then you essentially generate this complex low pass equivalent signal, and if you take that complex low pass equivalent signal multiplied by e power j 2 pi f0 t and then take the real part of it, that will give you the real band pass signal. Okay. So, that will give you the real band pass signal, and this complex low pass equivalent is sometimes simply called as the baseband equivalent signal or the complex envelope. Because this is already complex, you can write this as xi of t plus j x q of t, where you identify this I and q as the in phase and quadrature components. So, in phase component and quadrature components are again time varying functions, and the information is usually present in these two arms. Utilizing these two, you can construct first the complex envelope, and from the complex envelope you can construct the band pass signal. Okay. So, by substituting for x the complex envelope, x of t can be explicitly written down in terms of xi. Okay. So, this is xi of t cosine 2 pi f 0 t minus x q of t sine 2 pi f 0 t. Okay. So, this cosine term, that is the signal which is, or the function which is multiplying the cosine term, is called as the in phase term, and the one that is multiplied to the sine is called as the quadrature term. You can recover xi and xq independently by multiplying on one branch of x of t by cosine 2 pi f 0 t, and on the other branch by multiplying cosine with sine 2 pi f 0 t. So, what would that do? It would actually correlate these two and f 0 t, and then it would actually extract out xi. So, the output would be proportional, not exactly equal, but its amplitude will be slightly different, but it is possible for you to actually extract these signals, as you can verify from your communication system textbooks. Okay. So, this is what the equation wise was, but what actually happened out here was you started off with some pass band signal or the band pass signal which had centers at f 0, and then you can multiply this entire spectrum. If this is x of f, you can multiply the spectrum by a unit step function. Okay. A unit step function would be exactly 1 for f greater than 0, and it would be 0 for f less than 0. What it will do is it will eliminate this set of frequencies, right, and the result of applying this or multiplying these two will be a single spectrum which is centered at f naught. You can call this fellow as x plus of f, and next what you do is to actually shift this x plus of f onto the left by the factor f 0. So, if you take this x plus of f plus f 0, what you would have done is to actually push this spectrum which is originally centered at f naught onto center at 0, and of course, this x plus of f plus f naught would actually be in time domain look like x plus of t e to the power minus j 2 pi f 0 t, and once you have done this one, you have obtained the complex envelope x tilde of f. So, therefore, in terms of time domain, this would be the complex envelope x tilde of t. So, x tilde of t is x plus of t e power minus j 2 pi f 0 t, and exactly what is x plus of t? X plus of t is the inverse Fourier transform of x of f multiplied by u of f. Okay. I will leave this as an exercise for you to figure this out. So, we will wrap this module now and consider several other concepts in the next module. Thank you very much.